Nowadays, European researchers in regenerative medicine have made major advances to repair a defective eye or ear. Thanks to nanotechnologies, the general public will soon be able to benefit from these state-of-the-art advances. In Finland, like elsewhere in Europe, hearing problems among seniors are on the rise. For patients like Pekka Laikinen, difficulties in understanding persist even with hearing implants. Like this test in the ORL department at the Hospital of Tampere shows. Friction.
Friction.
Hedgehog.
Headgear.
Furious. Fur.
Sir? There's another setting here, but I don't use it.
Such misunderstandings can create a sense of isolation for patients who no longer dare participate in conversations. To remedy this, Professor Pico, project coordinator for the European project Nano-Ear, is striving to revolutionize inner ear medicine through the use of nanoparticles.
The goal of the Nano-Ear project is to improve or restore the auditory capacity of people who've experienced hearing loss. It actually consists of a technique based on nanoparticles, which are used to carry drugs and genes to a specific destination.
The nanoparticles designed in this lab are infinitely tiny chemical molecules. Their role is to deliver active substances to the damaged cells of the inner ear. Their nanometric size enables them to cross the cell membrane and deposit the drugs needed for cellular repair directly in the nucleus.
Numerous drugs are currently being tested for this kind of use, and these techniques will be conceivable for humans in a few years.
While waiting to move on to clinical trials, the composition of nanoparticles is verified through hearing tests carried out on unconscious rats. Another country, another organ. In France, nanotechnology is once again being called upon for the fabrication of artificial retinas. In this lab, the focus is on nanomaterials. These materials are well tolerated by the organism and transmit electrical information to the retina. When this chip is implanted in the eyes of blind patients, they recover a simplified form of vision.
We need a material that's biocompatible. We here at the DREAMS project are working on diamonds. This diamond is used directly as a semiconductor. In other words, it's a material that's electrically conductive, but not too much, and which can directly stimulate the cells of the retina.
The diamond used to coat the implants isn't a precious stone, but a synthetic material produced in this machine.
With this procedure, we make a diamond that can be even purer than a natural diamond. It's actually an assembly of tiny nanometric diamond crystals stuck together to form a whole, a continuous diamond film.
This implant, no bigger than the head of a pin, is connected to a power source. It was tested at the INSERM on retinal cells to make sure it could electrically stimulate the retina to replace the action of the photoreceptors.
This project is intended for patients who've gone blind, who've lost their photoreceptors. There are several layers of neurons in the retina, and when the photoreceptors deteriorate, there are only 2 layers of neurons left. The idea of the retinal prosthesis is to electrically stimulate these layers of neurons so they can send visual information to the brain.
The European DREAMS project team isn't there yet, but an experiment conducted with an American prosthesis that was implanted in 30 subjects has proven the procedure functions. The sole drawback, with just 60 pixels to compose the image, only shapes and colors can be recognized. The nanodiamond will increase resolution to 1000 pixels, finally allowing patients to get around on their own.